So much, Megan.
Yeah, thank you.
Thank you.
So should we proceed to the last talk, or?
Yeah, let's go ahead.
Let's go ahead. I think so. Okay. So the last talk will be given by Marta, and the title of the talk is Optimizing Biomedical Ultrasound Workflow Scheduling Using Cluster Simulations. This paper falls to the category of so-called open scheduling problems, which means that it describes some system that is doing some interesting things, and while doing these things, which Marta will explain, it has to solve some scheduling issues, which we are always interested in. So, Marta, welcome to JSSPP, and the floor is yours. Feel free to.
Marta, just confirming it's okay for us to record your talk.
Yes, I am.
Thank you.
Okay. Okay, can you see my screen?
Yes, yes.
Okay. So my name is Marta Jaroš, and in my today's presentation, I'm going to talk about optimization of biomedical ultrasound workflow scheduling using cluster simulation. So first of all, I'd like to give you a short introduction to the biomedical ultrasound workflows. Ultrasound is a very promising tool for medical applications like non-invasive surgery and neurostimulation. To maximize the outcome of the procedures, it's necessary to plan them precisely for each patient individually. In other words, be able to estimate and quantify the outcome for the particular ultrasound transducer setup. As you can see in the picture below or in the video, a tumor can be destroyed by applying a sequence of sonications, one by one, to cover the whole area in the issue. The computational process simulating the treatment can be described using a workflow, as you can see below in the red rectangle. From the computational point of view, we need to simulate for each sonication independently how the ultrasound wave propagates through the coupling medium and penetrates the tissue. Then calculate a heat map and evaluate the success of the whole ablation. The underlying physics is very complex and uses numerical models of the wave propagation. Since a typical simulation needs about 100 gigabytes of memory, it's not possible to use desktop computers or small servers, but we do need to use huge clusters like supercomputers. However, composing a workflow and its offloading to a remote cluster is quite challenging even for an experienced developer. Therefore, it is crucial to offer clinical end users a middleware layer that allows a treatment setup or other data to be uploaded using a simple interface and automate the execution. We designed and implemented this middleware layer using our software package called KDispatch. KDispatch is, however, much more than a simple submission system. It offers a high level of automatization by selecting an appropriate amount of computational resources and expected execution time for particular tasks. This is enabled by a fixed set of medical certified binaries that can be used within the workflow and the collected performance data updated after each successful run. This allows to estimate the strong scaling for particle binaries on the fly and tune the execution parameters to minimize the execution time or the computational cost. However, since the computational resources are limited and may be shared by multiple workflows, the queuing times can depreciate the execution plan. The ultimate goal of K-Dispatch is to provide automated, effective, and failure-free workflow execution. Many other tools have been developed to solve the task graph scheduling problem. However, we haven't found any that would take into the account the possibility of changing the amount of resources assigned to each task. Yeah. Designing a good or effective execution plan is very challenging. Since each task in the workflow is variously demanding and can be executed on different hardware with different execution parameters, there are really a lot of options how to map these tasks onto the computational resources. In practice, it's unfeasible to test all options one by one. Therefore, we need to use some heuristic to create a suitable execution plan. In the example number 1, you can see a task level optimization. In this case, the execution parameters are selected for each task independently, regardless of the current state of the chosen cluster and its computational queues. Such an execution plan is better than blind use of default execution parameters, but it still wastes the computational resources, and it can't empty spaces in the plan, as you can see in yellow in the picture. A more better way is a workflow level optimization, which you can see in example number 2. This optimization considers the current state of the cluster and plans each task sensitively to the whole workflow. K-Dispatch implements 4 performance modules to be able to create effective execution plans. Optimizer module finds the execution parameters based on the task inputs. To improve the optimization in future, small perturbation of the execution parameters may be done. For example, selecting 6 nodes instead of recommended 5. Optimizer can implement algorithms like hill climbing or simulated annealing. The next module is Interpolator. Interpolator can estimate the execution time and cost for a given amount of resources. We've already provided some primal experiments with linear and cubic spline interpolation, and we've received quite promising results. If the estimation fails, the task is executed with the maximum execution time, and we expect the next runs to be improved in the future. The next module is Evaluator. This module determines the quality of the execution plans In other words, it calculates the overall execution time, including queuing times, which has a great impact on the whole planning process. Therefore, we use the ALEA simulator, which we would like to integrate directly to K-Dispatch. We can provide ALEA with actual cluster data and simulate different scenarios. This can help us to improve execution plans a lot. We can also influence the overall execution time or computational cost by setting the W variable, as you can see in the equation below. And the last module is collector. Collector simply updates performance data that are stored in the database of K-Dispatch. This is provided after each successful run, and the optimizer helps better adapt to the cluster workload. I think at this point, it's very important to say that this approach is general for various code types, because this algorithm is based only on the collected data and collected data of strong and weak scaling, and on the input data sizes. Well, here follows a couple of experiments with the ALEA simulator. We used a neurosimulation workflow consisting of the processing tasks, which are simple and run only on one node, and simulation tasks which are very demanding. They run on up to 16 nodes, and they are in the majority in the workflow. You can see this workflow on the left. Then we defined a smaller version of the Ensemble supercomputer, which has 16 nodes, and each of these nodes has 16 cores. Below you can see the scaling data of the aberration correction simulation and forward planning simulation, which are the most demanding ones in the workflow. If we consider the W variable from the slide before, if we consider this variable to be set to 0.5, then the optimal solution would be depicted in green. It means the optimal solution is for 10 nodes. However, as we already seen 2 slides before, 10 nodes aren't very good for our system because we have only 16 nodes, and we can execute 2 of these simulations concurrently. So we performed our experiments with 4 and 2 nodes for these demanding simulations. The following experiments consider only one workflow running in the system at the time. So this is experiment number 1. As you can see, each of the simulation uses 4 nodes, and this is task level optimization, because each of the tasks has the same settings. The picture on the right hand side shows a Gantt chart. It's the output from the ALEA simulator. You can see that tasks are really executed in the order as we defined, and the overall execution time is slightly more than 30 time units. We use abstract units here. This execution plan was created on the workflow level. You can see that some demanding simulations are executed on 4 nodes and some of them only on 2 nodes. From the Gantt chart, you can see that overall execution time was even shorter than at the experiment number 1. The comparison between these 2 experiments is better visible on the 2 graphs on the right-hand side. Use time slots may be presented as a cost of the computation, and we can see that the experiment number 2 was better by 26%. So it was cheaper and faster. Well, and I'm approaching the finish of my presentation. So here are some execution planning challenges. And now I'm going to talk about the performance modules of K-dispatch. For the optimizer module, the big challenges are a selection of a fast algorithm, adaptation on a changing workload of the cluster, and multi-workflow optimization. How it will work if we run 10 workflows in the system. For the interpolator module, it's data filtering. I mean filtering by age, missing data, or detect some anomalies. Then reliable interpolation in a noisy data. For the evaluator, it's how to provide this model with actual cluster workload snapshots, how to adapt the plans to user priorities that are used on the cluster, how to set the backfilling parameters, and so on. And the implementation challenges are how to integrate the ALEA simulator, which is implemented in Java, to K-dispatch, which is implemented in Python. So, as a to conclude this presentation, here are some major sentences I would like you to remember. Workflow planning based on performance data has proven the ability to save a significant amount of computational time and cost. From our experience, it's up to 26% for a simple benchmark. We introduced a new architecture that is composed of 4 modules. An optimizer, it's added in the proof of concept stage. Interpolator is partially implemented and at this time is being tested on large data sets. Estimator, we just provided first attempts to integrate the ALEA simulator. And collector is fully implemented and it's routinely used for data collection in K-dispatch. Future work is evaluation of different optimizer strategies and deployment on real systems with real workflows. So that's it. If you have any questions, I would like to answer them. And thank you for the attention.
Thank you, Marta. Some questions? I have one. On the slide number 7, there was a spike in the cost. Yeah, on the computation cost figure, I can see that when you use 6 nodes, there is a spike for the aberration correction in the cost. why is it so? The task doesn't scale well at 6 nodes?
Well, 6 nodes.
It's in the right figure, you know.
Yeah, I can see it. I'm just thinking about it. Because it's not just the middle of the number of cores.
Okay, hi, if I can comment, I'm a third author. So the reason is the domain size is not evenly decomposed between all these 6 nodes. So there are different setup of transducers, basically the way how you inject the signal and some measurement points where you capture the signal in the medium. And this is basically not
could you come a little closer to the mic, please?
Oh, yeah, I will try it.
Thank you.
So maybe it's all about the work balancing. So I said that basically the domain size is not even distributed among all the cores in this case, because the definition of the sensor mask, which is the places where you capture the signal and the places where you introduce the signal into the domain, is basically on a single node, and this single node slows everything down.
Okay, thank you. The mic is fine, Marta. You don't have to.
Oh,
Yeah,
okay.
it is. When he got close, it was fine. Thank you.
Just
Okay.
the distance. Yeah.
Yeah.
I would like to add that since this is a this open scheduling problem talk, so we've discussed with Marta and Jiří that they will try to provide us some real data because they already have some reasonable knowledge about those binaries that are about their scaling and about the parameters that typically are used, which can be quite nice to have this kind of set of workflows about which we know quite well how they behave, and we can then put it on the website or something like that to provide us the real data, because the metrics are clear, the cost and utilization and make span and so on. So that was just to add. And I see that we have a question. Agung, can you please ask the question about task dependency?
Okay. Thank you for the great presentation. I have one question. Is there any data task dependency between the tasks, or is completely independent with each other?
No, there are dependencies between tasks in the workflow. If you take a look on this workflow, the tasks that are like in one row, they can be executed concurrently, but if you go in this way, there are dependencies. So
So there is task dependency.
Yes.
Oh.
Okay.
Yes, there is.
Oh, I see. So we cannot place the dependent task into different nodes.
Yes.
Oh, I see. Okay. Okay. Thank you.
Do we have some more questions? If not, we ended this session, but we ended it 20 minutes sooner than expected. So what we can do now is either have an early refreshment break, or if you would like to continue with another talk and then have the coffee break as planned. I'm not sure which choice is better or worse. So how do you feel, guys?
I think we should try to go do another talk, because then, like the second session was bigger than this first one. Since we have the time, we can just transfer one of the papers and then do 3 papers after the break.
Okay, I think it's good idea. So if I would like to thank Marta again. Thank you.
Yeah.
And
Thanks, Marta. Great work.
Thanks.
And the next speaker should be Roberto, and his talk is going to be about evaluating controlled memory request injection to counter PREM memory underutilization. So actually, it was Walfredo's task or Narayan's task to introduce this talk. So sorry, I let's skip you guys. But I can see you.
No worries. We are happy for you to do it, Dalibor.
That's work stealing, right? Like that's a well established.
Yeah.
Ink.
Yeah. So.
Okay, so can I share my screen because Marta is still presenting?
Oh,
Sorry.
now it's free.
Okay.
And
So
give me a second just for me to
stop the recording.